Very good afternoon. Very good afternoon. I hope the midsem paper was fine. The solutions will be discussed during the CRIP session, right before the CRIP session. How did you find the midsem paper? Was it too easy, too difficult? Sorry? Yes? Any volunteer? Moderate? Okay, that's fine. So the pace at which we were doing proofs for analysis, convergence analysis before midsem is not going to be what the pace is going to be now. Because I think we have done enough. We have a fair idea of how these proofs are done, right? So what we will plunge into starting today is a lot more algorithms, right? So we want to really complete several algorithms in the next 3 or 4 classes. And of course, the first step would be understanding what are the possibilities, what are the gaps, right? What are the combinations we have tried so far? What combinations of functions, right? Smoothness, continuity, Lipschitz smoothness, Lipschitz continuity, convexity, strong convexity. What combinations have we explored so far? Yes. The first was convexity plus Lipschitz continuity, right? What was the second one? Did you directly jump to strong convexity? Convexity plus? Convexity plus Lipschitz smoothness. What was the third? So we tried to add strong convexity and persisted with Lipschitz smoothness because the most attractive part is that you're putting a lower bound and an upper bound both, right? On the curvature of the function, right? And what else did we do? We considered these combinations. This was the last one we considered. So very briefly, right? What were the resultant? Yeah. What were the resultant convergence analysis? For a smooth and strong convex function, we possibly got the best, right? So far, at least. And that was, we always characterize it in terms of a sufficient condition, right? The other was about sufficient condition. So what was the sufficient condition? You need, not you need. If you have T greater than or equal to some L by mu, L is Lipschitz smoothness, mu is a strong convexity factor, log of, and this was the attractive part, log of R square, which is R is the distance, the upper bound of the distance of the initial iterate from the optimal solution, R square L divided by 2 epsilon. So this log of 1 upon epsilon was a very attractive part. Okay, now we'll see what it means in terms of errors. So if you want very small error, 0.01, you'll need fewer iterations. Right? So if you had only smoothness with convexity, you would require of the order of 50 R square L. Basically, we'll see that it was 1 upon epsilon. Right here it is 1 upon. So this was 1 upon epsilon square, convexity plus Lipschitz continuity. This was 1 upon epsilon, which is convexity plus Lipschitz smoothness. And now you got log of 1 upon epsilon. So this was where we concluded. And in the midsem, one of the problems was about Bregman divergence. So right, I give a very simple problem. The condition of Bregman divergence there was equivalent to strong convexity. I hope you got this answer. That's the last one is what you should have got. Of course, Bregman divergence is used in slightly more. There are twists to Bregman divergence, largely through treatment of distributions on functions. But for now, it's just a strong convexity condition. So summarizing all of this, right? Where are we? So if we just take a hypothetical example, L is B equals L is B is 10, R is 1 and mu is 1. So if you set epsilon to 0.1, then SS, this we have an abbreviation for this. We are calling it SS. Smooth and strongly convex case would need only 8.49 iterations, whereas S, which is the previous case, which would require 50. This is S. Convexity plus Lipschitz smoothness, right? Of course, we are not even discussing convexity plus Lipschitz continuity. We're not impressed at all. But yes, for completeness sake, we have it R square, B square, by epsilon square. But here, I have not really listed. Oh, there is, sorry, I've done that. Okay, done that. So that is called C. Oh, by the way. This looks ridiculously large, right? For epsilon 0.1, C is 10,000. Right? So you see how better we are, right? I mean, now increase epsilon, decrease epsilon by 0.1 at every step. And you find that you're adding only a constant number of iterations, which is very impressive, right? The log of 1 upon epsilon means that from 8.49, you need 13.49 iterations. And epsilon decreasing to 0.001 only increases the number of iterations by 5 more iterations. Right? So this is the additive constant part is the most attractive part. So that is why, right? So this, you see the very embarrassing situation here with C. C is every time increasing by by a factor of 100. S is increasing by a factor of 10, whereas SS, strong convexity plus smoothness, is by an additive constant. So that's called linear convergence. So you're of course welcome to revisit those slides again. This is basically what we refer to as a Q-linear convergence. We have pretty much got linear convergence. Linear convergence is when you have this additive constant. Okay. I had on the Moodle I had also put out some collab notebook, right? I hope you saw this. Listen, the mouse is not working. I don't know why the mouse is not working. Okay. Okay. So this is a Python notebook, Colab notebook, which I shared. I hope you've seen this. Any of you saw this? I put it on Moodle. So this was also showing the effect that these different conditions on the step size have. While we only talked about the gradient descent under different conditions of the function, but here for this SMS spam data set, what we also show is the convergence, practical convergence, which also depends upon the step size, choice of step size. So I begin here with, yeah, this is, you see what I talk about is function evals, right? Number of function evals, but this empirical function evals counts and the function values and the condition on the alpha, the step size under different step size choices. So this is printed. I think the first one is just a very naive, right? Then we look at what we call the RMO. So RMO conditions, and we again measure this, right? The number of backtracking steps, number of function evaluations, and so on. And you see that we get better with more sophisticated. So the most sophisticated is when we have these strong wolf conditions. I think there is also the strong wolf condition printed somewhere down. So feel free to, right, the number of backtrackings, for example, here is just 5. Right? So and yeah, here you have this plot, a summary of all of these. So RMO condition V4, which put together many of these strong wolf conditions, converge pretty fast. So in practice, on the other hand, you find the blue one, which is fixed alpha, which is not at all impressive, right? The blue curve. I mean, it's not impressive compared to what is possible with V4. There's a RMO condition V1, which is just a very simple Goldstein condition. And you find that is, so if you don't put the right condition, again, you may be worse than just a default alpha. So this kind of plot summarizes. So in practice, this is not sufficient, right? You also need to have the right step size. But this also matters, right? And we'll show a little bit more on why this analysis, convergence analysis matters today. Okay, so the perspective you're going to bring in today is what about some of the missing combinations? What's missing out here? So one perspective is look at missing combinations. And can those missing combinations also reveal more? So what's missing out here? Strong convexity here. Right. So strong convexity and Lipschitz continuity. So do you recall that there was something strange about this combination? So try and recap, right? There's something challenging with this combination. We'll see that a little bit, but you should think of it, right? So can a function be both Lipschitz continuous and strongly convex? That's a question. Do you recap? Right? See, this is a practical usage because you can't keep insisting on differentiability every time. Strong convexity is very easy to get without differentiability even, right? Just need to slap a regularizer. Whereas Lipschitz smoothness requires differentiability. So therefore, continuity is retractive. This is one reason why we are interested in this, right? So this is useful, but is it feasible? Okay. So unfortunately, the answer is no. Why? We have seen lots of examples. You'll need to somehow restrict or bound the domain. If you bound the domain, then you can possibly talk of both, right? You've seen examples. So unless we consider restriction of the function, this combination is a bit challenging. That's what I've highlighted there in green. So on a bounded set, we could possibly talk about that. Basically, the gradients are also upper bounded. if you have bounded set, the gradients will also be upper bounded. Right. So for example, norm of W square is less than or equal to R square. So within that, like, can possibly talk of um, um, the combination feasibility. Right. So if now a classic case for us is hinge loss. Hinge loss is Lipschitz continuous but not smooth. So hinge loss plus a regularizer, which will bring lambda norm W square, which will bring you strong convexity. But to make the combination actually work out, you need to add norm of W square is less than or equal to R. Okay. Um, so we'll very quickly go through what happens in this case, right? Can we get better? Does this give you best of both worlds? I mean, can it give you something between so best of both worlds in the sense? What was good about the first combination? It's very commonplace, right? What is good about um, the strong convexity part is that it has given you much better convergence. Can you actually get it to log of 1 by epsilon just based on strong convexity without Lipschitz smoothness? What do you think? Do you think you can get 1 upon epsilon here? Sorry, a log of 1 upon epsilon? Obviously, we would expect to perform better than 1 upon epsilon square. That's right. So, so the other extreme is 1 upon epsilon square. So somewhere in between the two will you land? That's the question. Right. So certainly we want, as I said, an improvement over 1 upon epsilon square. Okay. So it turns out that we can actually get a 1 upon epsilon bound. So which is like convexity plus Lipschitz. So strong convexity plus Lipschitz continuity becomes analogous to convexity plus Lipschitz smoothness. I mean, analogous modulo, obviously, some of these constants, some of these factors. But there is another reason we are taking up this case. It's not just for getting to another example of 2. We are also interested in this because we're going to analyze gaps. So there are some worst case gaps that have been proved in literature. And we want to see if, and for all these class of functions, the worst case gaps and what we get, right, the sufficient condition. Is there a gap between them? Is there something we can do in each of those cases? That's the other reason we want to complete these combinations. So with that motivation, right, as I said, we will be able to establish. Now, this is more of an existential thing, as I said, right? In all these cases, we had to minimize with respect to some the step size, right? At some step, where there was an inequality. One of our favorite tricks was to, when we had a lower bound, you would try and maximize it. When you have an upper bound, you would try and minimize it. So we showed that there exists a case when this happens, right? If you take a sloppy choice, you're not guaranteed 1 upon epsilon square or 1 upon epsilon, 1 upon epsilon square even. So we'll do the same thing here. We'll get to 1 upon epsilon. T is greater than or equal to something of 1 upon epsilon. But the proof technique is going to be even more specific. We'll find some choice of step size. And we will not spend too much time on how we can generalize that proof. There are ways of generalizing the proof. So just bear with me. Okay, so in this case, I'm just going to call out the important steps, right, without getting into details. The tricks we are invoking. The first trick is, of course, our favorite trick, which has to do with writing a dot product as a quadratic expression. And then we also had so this is first one was algebra. And then we used for Lipschitz smoothness, this property of the dot product being greater than or equal to something expressed in terms of strong convexity. So we are bringing back strong convexity, right, from our previous S3, from the SS, which is combination 3. So we bring that back. And so then we basically get a term which involves on the right hand side a difference of fx star and fxt plus some quadratic term involving xt and x star. Now, what we will do next is Lipschitz continuity. Right? So we have not used Lipschitz continuity, so we can bring a Lipschitz continuity that this term is bounded, so that so the color coding is probably showing you the correspondences very easily. Um, the other part is 1 upon mu gamma xt minus x star, and then there's a term involving xt plus 1 minus x star. I've just brought them to the same side. So some rearrangement. Now the next step would be as I said, this is just rearrangement. What we will do is we will take a gamma t which is specific to the choice of t. Okay, so gamma t which will be a function of t. As I said, for this specific proof, we are showing that there exists a gamma t for which we will be able to get 1 upon epsilon. Okay, so we'll do a scheme with t specific gamma t to make things work basically. But there is a way you can a longer proof where you can generalize beyond this choice of gamma t. So next step, right, is telescopic coming. That's something we have not used so far. That becomes useful, especially because we have got this xt and xt plus 1 all on the same side, right? So, but to get to telescopic summing, you'll have to do some multiplication, right? Because they don't have the same factors. Okay, so the two things we'll do: we'll bring in a specific choice of gamma t here for making some of the cancellations effective through telescopic summing, and the second trick we'll do is do some multiplications, right? Okay, so the first trick, as I said, is bringing some gamma t. As I said, this existential. So if, let's say gamma t proportional to 1 upon t was also kind of used some time back. So there's going to be gamma t proportional to 1 upon t, and then bring telescopic summing. In fact, the choice is mu into 1 minus t. Mu is coming from strong convexity. Mu into 1 plus t divided by 2 is gamma t inverse. Right? So basically what does this mean is basically meaning that gamma t is 2 by mu into 1 plus t. And now little, as I said, the next step is a little bit of more algebraic manipulation through some use of some multiplicative factors. So there are multiplicative factors when you actually bring in gamma t inverses mu into 1 plus t by 2. So you'll start getting this t into t plus 1, right? All these. But if you actually start expanding, you will find that cancellations actually are effective. So with all the hard work you do, you'll end up getting that t times f xt minus f x star summed across all values of t will be less than or equal to t b square by mu. Capital T b square by mu, the right hand side. Okay, just take it, assume that this works out, because as I said, I've really cherry picked my gamma t. On the left hand side, we will, as usual, do a lower bound, right? When we have summation of xt minus x star, f of xt minus f of x star, then we really find the worst case, right? The worst case, it's a lower bound. And the worst case is based on the final xt. Okay, so, or basically the xt that minimized. Decaying step size, yes. Yes. You can get. Just that the proof is a lot more involved. So we're just showing that there exists. So this, as I said, today's goal was to show that for some choice, this can be achieved. I mean, for all, as I said, even for the previous ones, if you chose a sloppy gamma, you are not guaranteed 1 upon epsilon. So all this is existential in some sense. So I'm just keeping it short. The story is short today. But thanks, very good question. Please do ask questions. I think it's okay if we are skimming over the details, but I think the high level understanding is important here. Okay, so with all of this, we'll end up getting, as I said, in fact, so here on the left hand side here, t into f of xt minus f of x star is less than or equal to f, t b square by mu. The challenge, of course, is while I can lower bound the left hand side, try and lower bound the left hand side, there is a multiplication by t. So this is very tricky. I mean, even with our cherry picked gamma t, it is I mean, it's not so nice to look at, right? The left hand side. So we know, of course, we'll assume that f of x star is less than or equal to f of xt, which is less than or equal to f of xt minus 1. So we'll assume that the iterations are resulting in decrease in the value of f. So based on that, you can do a little bit of tricky, I mean, little bit of trick where you say, first of all, I replace this xt here with x capital T. X small t is replaced with x capital T. I'll keep this t as it is, right? So if I do that, then I can still guarantee that t small t into f of x t minus f of x capital T minus f of x star is less than or equal to the summation of small t into f of x small t minus f of x star. And then what I'll end up getting is a constant f of x t minus f of x star, which comes out, and inside the summation is summation over t, which will basically lead to t into t minus 1 by 2. Okay. So with all of this, you'll get, yeah, I think I'm going to, so this is important, right? So if I want the error to be less than epsilon, we'll need capital T to be greater than or equal to 2b square by mu epsilon minus 1. So we have landed up getting 1 upon epsilon term. It is clear? So there's an existential proof, that's all. Okay, so what do we have now? We have added one more to continuity plus Lipschitz smoothness. So here we have strong convexity. So convexity plus Lipschitz smoothness gives you 1 upon epsilon, and so does strong convexity plus Lipschitz continuity. So you can use S for both, right? Smoothness and strong convexity, both of them with a more relaxed version of convexity or continuity give you 1 upon epsilon. And then I've just presented the same old number of steps, right? We still have the same problem. Of course, convexity has been common in all of this. As I said, convexity is very good to motivate how fast algorithms would converge with respect to the other condition, which could be Lipschitz continuity or smoothness. So even without convexity, observation is that smoothness gives you better convergence in general than continuity. So convexity can be used as a tool to analyze rather than as a constraint. The other important thing is smoothness, I mean, has yielded overall less wall clock time. But there is issue that even with smoothness, here, right? Even with smoothness, there is still 1 upon epsilon. Smooth function gives you still 1 upon epsilon, even with convexity. So smoothness with convexity in general gives you less wall clock time than strong convexity plus Lipschitz continuity. Just an observation with respect to, see, you saw the strong convexity plus Lipschitz continuity, we had to cherry pick your gammas and all that, right? So you hopefully can believe that this, in terms of wall clock time, our new guest, right? The left LHS has less wall clock time. You understand what is wall clock time, right? So the actual time that is required, then the RHS. Yeah. Okay, I think with this we are now set to look at the next aspect, which is, can we do better in some of these settings? Are we really saturated? And wall clock time wise, certainly not. There's something new that's happening all the time. But in terms of analysis, are there gaps? Okay. So it turns out, and this is, I mean, I've given you reference to a paper here. It turns out that there are gaps. Okay, so let's understand this slide a little carefully. And in fact, I have presented there in the slide with respect to epsilon connection with T. Right here, I have written in terms of T in terms of epsilon. Okay, so you want to just do the equivalent here. So when you say T is greater than or equal to 1 upon epsilon square, what does this mean? Let's focus on the board. This look at the slides a little later. Let's write this so that you can compare what you've written on the board with the slide. So T greater than or equal to 1 upon epsilon square is like saying that if epsilon is what about the second one? So I'm going to erase some of this. So what's it here? Epsilon is right 1 upon T. And here what would it be? Yes. So let's assume this is log to the base 2. So what would you say? Epsilon is greater than or equal to? Yeah, I mean, the base is something we will discuss here. It doesn't have to be 2, but in fact, if you look at KS4, smooth and strong convex function, you possibly get an idea. But it's okay. I mean, there's some base. Let's just call it base B. The base part, I'll leave it as a placeholder. So B raised to T. I'm sorry. 1 upon B raised to T, right? Some base T raised to T, and of course, there's some constants here. Some other factors here. Okay. Sorry, that was 3. We can erase 4. 4 is already. Okay, so now what you see on the slide is what are the lower bounds. Now these lower bounds are typically determined by looking at some pathological function. So what we understand by lower bound is any black box procedure will have an error of at least epsilon will be at least RB by 2 into 1 upon square root T. Right? What does that mean? That, well, there exists a function. If you give me a black box procedure, I will give you a function which will actually make the life of that black box procedure miserable. Right? That's what it means to come up with an adversarial pathological function. So the pathological functions could be different for different classes. In fact, it's possible that I have a class of pathological functions and I pick from one of them. It's not that, because depending on the black box, I may actually want to give a host of pathological functions, say 5 pathological functions, and I'll guarantee that your black box procedure will yield an error of at least so and so, the one in red, right, for at least one of those pathological functions. You understand? And these pathological functions are not at all nice to look at. Okay, so you are welcome to look at these this PDF. Very, very contrived. Okay, so but the interesting thing is they give you these lower bounds, right? The error earlier we were looking at like upper bounds. So so the error will be at least. So we are doing a comparison there. In gradient descent is RB by square root T, so order of square root T. This will be at least RB by 2 into 1 upon square root T. For Lipschitz continuity, again look at there. There we had 1 upon t. Here it is 1 upon, I mean, it's actually t minus 1, but it is 1 upon t again here, right? B square by 2 mu t. So these seems to match. These both seem to match, right? Square root t is 1 upon square root t, 1 upon square root t, 1 upon t, 1 upon t. The third case, this is interesting. Well, this case 3 is actually numbering is different, no? So the case 3 is basically maybe I'll just do a numbering change. So this is case 4. So I'll just a small numbering change. This is case 3. A strong convexity plus. Oh no, did I? Okay, I think I swapped it. So this is case 3, and this is case 2. Not a problem. Case 2 and case 3 are the same, right? At least as far as our analysis is concerned. So we just finished case 2. The proof we did some time back was for case 2. Strong convex functions plus Lipschitz continuity under in some bounded domain. That was 1 upon t minus 1, and it turns out the worst case is 1 upon t. Smooth functions is what we did maybe 2 classes right before mid-sem. Smooth functions plus convex with convexity. So it turns out that we get 1 upon t here. We have shown 1 upon t. We have recapped. It's 1 upon t here. This is also 1 upon t. But it turns out, this is the interesting part. It turns out that the lower bound that have been proved in literature is 1 upon t square, order of 1 upon t square, or 1 upon t plus 1 square. So you see there's a gap here, right? We see the worst case is only 1 upon t square. That means actually possibly I can do better. Can I bridge this gap? A gap between lower bound and actual time. Is this clear? In the other 2 cases, there is no gap. This looks like a gap. In fact, even in the 4th case, case 4, which is strong convexity plus Lipschitz smoothness, what we had earlier, the log thing, right? So now the base is becoming a little clear here. So base here is 1 minus mu, 1 minus mu by L. So the base B, I kept it as a placeholder here, right? So this base B is being shown here. In fact, yeah, it is. 1 minus mu by L. So in fact, 1 upon B is 1 upon. Maybe I should put 1 upon B. What was mu? Mu was the convexity, strong convexity factor. L is the Lipschitz smoothness factor, which is supposed to be higher, mu or L? Yes? L, right? We know that. Mu is less than or equal to L. Mu is a lower bound on curvature. L is an upper bound on curvature. Right? And if you insist that a function is both smooth and strongly convex, you would necessarily have mu is less than or equal to L. So 1 minus mu by L will be between 0 and 1. So that's the base here, 1 minus mu by L. Very intuitive base, right? And you can think of, I mean, you can rearrange this using this kappa. I think kappa is L by mu. Kappa is L by mu. Okay. So you can rearrange it if you want. But the point is, the worst case, it turns out, is not very different. The worst case seems to be having this kappa, square root kappa minus 1, blah, blah, blah. It's like the base. But the exponent is of similar nature, which is t minus t, right? I mean, this square root kappa minus 1 divided by square root kappa plus 1, the whole squared. Think of this as its base. the 2 can be also pulled into the base itself. The exponent still remains t minus 1. Is this clear? So the gap, there is no apparent gap here either. I mean, you can, if you want, you can think of this also as some gap. Certainly there's some gap here relative to cases 1 and 2. So case 4 does display gap relative to cases 1 and 2. But it is not as bothersome as the gap in case 3. Is this clear? Okay, so right, so the point is, so I've written the same thing differently, right? T greater than equal to 1 upon epsilon square, t greater than equal to 1 upon epsilon. And here basically we are saying that in case 3, it was supposed to be, right, this case 3. It was supposed to be t greater than equal to 1 upon epsilon, but the worst case is t greater than equal to 1 upon square root epsilon. This is saying t is greater than equal to 1 upon square root epsilon. So this is where we identify scope for improvement, the case of convexity and Lipschitz smoothness. This makes sense also. See, we are not seeing a gap in our new guest. What was our latest entry? Strong convexity plus Lipschitz continuity. We didn't see a gap. Well, I mean, our proof was so contrived, right? We cherry picked the value of gamma. And in practice, this is difficult to achieve as well, right? I mean, we bounded set, etc. So I just by the nature of the proof, I wouldn't have expected a gap to be here. But this seems to be a class apart, convexity and Lipschitz smoothness. And apparently that's where there is more scope. Is this clear? This summary? Okay, so what is the question we are going to ask now? Can the gap between lower bound and realized bound motivate an improved algorithm, improved set of algorithms in the case of Lipschitz smooth plus convexity. So Lipschitz smooth, remember, we are trying to put an upper bound on the rate of change of the gradient of the function, or kind of an upper bound on the curvature of the function, right? Now our algorithm never looked at the curvature. Our algorithm never looked at how the descent iterates across iterations were behaving relative to each other, right? We didn't really care. I mean, if it was a lot of descent in one step, next descent was very less. We should have probably scratched our hair and said, well, is everything wrong? Correct, right? I mean, so you can accelerate gradient descent based on the curvature of the function. That is the insight we get from this gap, right? And improved. So the improved set. So it's an improved set, not just one, right? So accelerating gradient descent. So let's get ideas from all of you, right? What would you accelerate gradient descent using? Using the learning rate, you'll accelerate gradient descent? Okay, so you're talking still about, so there are two things, right? At least two things. One is the direction, and the other is the step size. Is that what you mean? Now, by learning rate, you mean step size? So you can, yeah, you can look at the step size itself. But isn't direction a little bit more fundamental? If I have the wrong direction, what can step size do to retrieve or escape, right? So yes, both on both sides, both fronts you can. But unfortunately, step size is something that you can't avoid engineering in step size. Be very honest, right? So learning rate, the schedule associated with learning rate is a lot of engineering associated. Whereas direction is a little bit more fundamental, possibly should come from analysis itself, right?
It already gives us the direction towards the lowest top. So how are we going to optimize direction?
But gradient descent is giving you a direction of descent at that iteration with respect to that iterate. What we are saying is, if I knew how the function was behaving across several of the previous iterations, the behavior of the function cumulatively might give you some idea of the curvature. That is what smoothness is about, right? So the direction part, right, is aggregate behavior of, say, curvature. I'm just putting curvature in bracket. That's motivated from smoothness. This is across iterations and not just that iterate. Is this clear? Okay. So this is our foray into accelerating gradient descent. So gradient descent has suboptimal rates, and the suboptimal rate is exactly what I talked about here. When you have Lipschitz smoothness and convexity, we were saying 1 upon t, lower bound says 1 upon t square. Right? So 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 what about lower bound? So the observation was that gradient descent just lies on local gradient information. Your question is, what is wrong with gradient? It's too local, right? And when we look at an aggregate view, we are looking at how it's behaving cumulatively across iterations. So can we add some momentum? So momentum, I say curvature. The curvature basically is an outcome of, looking at the first order moments, right? I mean, a lot of the first order moments can give you an approximation to the curvature. I mean, a curvature may also need second order moments, but I'm approximating the curvature using some first order moments. That's where momentum comes in, right? So you can see in this, I'm just highlighting here, right? So this, in this figure, you can see, unfortunately, if I have to converge here, I'm going a lot of zigzag. Right? So your point, right? What is wrong with, let me zoom in here maybe. Oh, I'll have to. So let me zoom in here. The collab notebook also, you can see some of this happening, right? So you can see if I take this gradient step, I'm possibly overshooting already. I had to go to the black point, but I've actually overshot, right? So the fact that across these multiple local myopic descent steps, there's a lot of cancellation, right? You're basically cancelling out effects. The step number 2 is cancelling out some of the effects of step number 1. Now, if I factor in that cancellations and look at the momentum is where, right, across all of these, the momentum is actually towards this direction. You understand? So these redundant computations could be adjusted for each other using the momentum. That is the whole point. Right, so I'll try and zoom in here again. Okay, so here, if you see this figure, so you are moving in this direction once. This is visible clearly, or should I try? Yeah, you were moving in this direction once, and then this direction. So if you average them out, you're basically getting the yellow highlighted direction. That's the average movement, and momentum. Okay, so that is why just step size is not sufficient. Hmm? Okay, so iterate is basically step size plus direction, but we are more focused a little bit more on direction. So motivation 1 is bridging the gap, and that the gap could have been worse for some other function than Lester. So all these lower bounds have been shown by Lester. Okay. Now, I mean, he came up with a pathological case, but there could be other cases as well. I mean, nobody says that that's the only pathological case. Right? So that's motivation. I mean, so that means there's potentially more scope. And the second is the previous iterates themselves. It's a very intuitive thing now. Whether it helps only case number 3 or even cases 1, 2, and 4 is open for discussion. It's possibly going to help others as well. This insight. And that the series of previous iterates could they influence the next iterate? That's the main question. Okay, so with this, what would the exact steps look like? Right? As I said, there is no one solution. There could be multiple. We'll at least look at 2. Um, any thoughts on what the variants could be? I said there could be at least 2. Yeah, we'll move to Adam, etc. That's what will come next. But instead of just throwing names, what conceptually, what are the different variants? When I say motivate an improved set of algos, right? What does a set come from? What are the alternatives, options, right? So while we say momentum, this momentum is being used in a very, as I said, it's kind of generalizing moments. So momentum in that sense is not the physics momentum, right? Physics momentum is only a function of mass and velocity. So don't think of momentum as that momentum alone, right? It's moments accumulated. So what are the moments you can think of? Right? When you can think of first order moments, they are like velocity. Also think of acceleration, which is like a second order moment, right? So that's what I'm saying. So whether you consider, when you consider velocity, when you consider acceleration, at least gives you some choices. I'll get into some details now. Is this clear to you? So the improved set could be thought of as resulting from So acceleration is second order. Velocity is first order. Okay, I think there's sufficient motivation. Now let's look at the specifics. So what I'm going to do is use this figure on the left hand side to illustrate. Is it visible clearly or should I enlarge it? Visible? So you can see that you have a red point, and from the red point, I need to move forward. Okay, so this on the horizontal, you can see something called gradient. On the along the y-axis, you see something called velocity, right? The actual step. So the actual step could be based on two things, right? One is, of course, what the gradient direction is saying. The other is what the velocity is saying. Velocity is accumulating from previous steps, right? So based on both of these, I can take an actual step. So that is called moment. That is momentum accelerated. Sorry. So x act is what happens after the actual step, which is x old, which is at the current step, plus v hat. Right. The v hat is the velocity, the one in green. So what is v hat itself? So I'll put the annotation. This v hat itself is accumulating from a previous v. See, remember, when I say I'm accumulating, now the v hat is coming from the previous accumulation. So you're moving along v hat, which is mu v. So this v hat is basically now contributing to velocity for the future, right? Minus the gradient at the current step. So this gradient at the current step is what you typically consider. You typically don't have, see, in gradient descent, this is not used. Mu v, mu set to 0, right? All of you agree? Maybe you can use the board now. So the x act or the actual step I'm going to take is x old plus v hat, and this v hat itself is mu times v minus the what we conventionally have as a gradient descent step. I just use eta k. Let me put it in white. Eta k instead of gamma. So don't get confused by notation. Since we are having many more components, we need to have more scalars, right? So eta k is a scalar, mu is a scalar, and we'll start seeing the connection with gradient descent immediately. So this is a gradient evaluated at the current step. So if you okay, in fact, that is something I'm going to ask, right? Where should I evaluate this gradient? I could evaluate this gradient at x old. I could evaluate this gradient at x old. If I evaluate the gradient at x old, then and if I set mu to 0, what do I get? If mu equals 0 and the gradient evaluation is at x old, then what will I get? Huh? Standard gradient descent. Okay. Now, question of course is what happens if I evaluate the gradient at some other point? I'm not bound to evaluate the gradient at the old point alone. Okay, so that's a question we'll come up with next. But at least we have, let's for the time being assume that x old is what is used for evaluating gradient. Now what have I done? By adding a mu which is non-zero, I have added momentum, right? Now the variants come based on where I evaluate x old, what the values of mu should be. Obviously, mu should not be 0. Eta, of course, is I mean, eta is going to be just the old step size. So with RBO or strong wolf, so most of the times proofs will require some condition on eta, right? So RMO strong wolf conditions are typically used. Though in some of our proofs we didn't do that rigorously. I'm going to give you proof for convergence of accelerated gradient descent. I won't prove it in the class, but I have my detailed notes, and there we have considered the most general case. You look at that proof and you probably get a headache. Okay, if you don't get a headache, I mean, you probably meant to take this field further forward, right? But it's very complicated. The moment you start putting all these conditions, but that's how generally these proofs are supposed to be, right? Use the most generic conditions. So eta is going to be for us a kind of black box. We will not concern ourselves with eta right now. Okay. Okay, with that, I think let's get into some more details. So now question is, what should mu be? As I said, mu, if you set it to 0, then there's no point. Should mu be 1? What happens if you set mu to be 1? I mean, you have to, of course, also anticipate what the V would be. V, as I said, is coming from the V hat of the previous iteration is possibly the V right now, right? And so think of that previous V as having its own gradient factors. So if you set mu to be very large, basically 1 is bordering on large, then all the previous gradients will eclipse the current gradient, right? I mean, you had after all something nice to say about the current gradient. It was at least the local descent direction, but you don't want to kill the local descent direction altogether, right? So if mu is large, and for us large is 1, right? Then what will happen? Previous gradient descent steps will start dominating. Then it's no longer, it's like anti-gradient descent. It's not in the spirit of gradient descent itself. So this is something again we don't want. So these are two cases we don't want, right? So that is the reason the recipe here is mu is between 0 and 1. So this mu is between 0 and 1. I hope this logic is clear. Now the next steps, right? So I kind of have brushed under the carpet the fact that the gradient itself could be computed at some different point. We have started with gradient at the previous iteration. Okay. So in plain text, right? What is V? V is playing the role of velocity. It's the direction and speed at which the parameter xi is moving through the parameter space, or in this case, W or whatever, right? Some parameter. Now, the other thing I want you to realize is this mu. Mu is basically an exponential decaying factor, because the V's will keep getting accumulated, right? So if you have the mu sitting here, and tomorrow, you'll again use a mu for V hat, right? So the next step you'll have a V double hat is mu V hat minus blah blah blah, right? This mu is basically serving the role of an is a decay factor and exponentially decaying. So that is the other reason mu cannot be 1. I mean, mu should certainly not be greater than 1. But mu being 1 is also a problem. Basically, then all the as I said, the same point, all the previous steps will will dominate. There has to be a decay. I mean, if a step was, if you already moved 20 iterations, right, why should the t minus 20 matter as much as the current iteration? So, I mean, it's the same point I've stated, slightly more magnified. So we would like it to be a decay factor, an exponential decay factor. Right. So the physical analogy, I already gave you one way of looking at it, which is right, the first and second order moment. Basically, a negative gradient is a force which is actually moving a particle through parameter space. Right. But as you move the particle through parameter space through the immediate gradient, the immediate force, we also have the velocity of the particle itself playing a role. Right? That is what we are abstracting away into momentum. So when is the step size largest? So there'll be a lot of fill in the blanks. Like I've been using fill in the blanks to help anticipate what might come. So when is the step size largest? So the two are aligned, right? Right. So when the gradient and velocity are in the same direction, or that it's not just one, but successively gradients are in the same direction. That's what we are meaning, right? Because the velocity itself is a compressed signature of the step so far, right? So step size is largest when many successive gradients point in exactly the same direction, which was not the case in the figure we showed previous slide. Okay. Now, yeah, so I've just tried to illustrate the same thing. Now there are options we are going to, now we'll open up some options, right? So I said this gradient f can be evaluated at different steps. You can say I will take an update, I'll make an update and then evaluate gradient at the new update step. Or I'll evaluate gradient at the previous update and then apply velocity, right? So there are two options you can see there. I mean, it was implicit in the figure, but I've made it a bit more clear here. So option 1 is where you say, oh, I'm going to take the gradient step, right? And then add a velocity. So so think of shifting this green arrow here, right? I'll take a gradient step and then add velocity. That is equivalent to saying that x is x old. This x is x old. The second option is I will assume that, okay, there was a gradient with some implicitly I've taken a gradient with respect to the earlier step, add the velocity, and then update the gradient for the actual update. So option 2 is basically saying that you take the gradient at x nu. And what is x nu? X nu is basically momentum with the previous gradient. Is this clear? Of course, I'll present it in more detailed manner. This is just an intuition slide. Okay, so don't, I mean, you can't just do direct substitutions here. but you can either defer the gradient evaluation post the velocity, or you can do the gradient evaluation and then add a velocity. That's broadly what we are talking about. So let me write down this intuition on the left hand side. So try to summarize all that we have found so far in the discussed so far. Right? We have decided we need exponential decay, which amounts to this mu being in the open interval 0, 1. But then I can have gradient descent at the old iteration followed by velocity with exponential decay, or do a exponentially decaying velocity update with respect to the previous iteration and then find a new gradient. Right, so that's what I've used, highlighted here. This option 2 is the one in blue, and the one in red is option 1 here. Okay, and what you can see here is if you were at a point like this, right, unlike the figure I showed earlier, here if I'm at this point, then all the successive iterations are in the same direction. They're all aligned, right? So this is a good situation to be. If I were here, for example, a different point here, right? That's what I showed earlier. Then I might land up going up and down. So step size is largest. So that's the reason I said step size should be a second consideration, because you would like to make the step size when there is alignment across iterations and not otherwise. Okay. Now we'll get into some more specifics. And the figures on the two figures you see now are the actual things that we'll consider. The first one is called the momentum update. So we have used momentum very broadly so far, but we are getting into specifics here. So first is called momentum update, where I compute the gradient at the current step, right? The option 1, compute the gradient at the current step, and then add a velocity component. So it goes by the name of heavy ball or Polyak momentum update. So those are names. On the right hand side is option 2, where I add the velocity with respect to the previous update. So you'll have to actually now keep track of what was the previous update in option 2. Okay, we'll see the details soon, but a little bit more work is required there. And then I'll add. So you see, just see what's the animation, right? I've gone to new and then computed gradient there. So directions can be very different. Okay. Actually, what I'm going to go do is I'm going to get started, but give you the homework. I think the homework problem is to really write down the steps. How would you? So what does it mean to actually realize option 2? Right? What does it mean to say I will add velocity to the previous iterate? So as I said, you'll have to do some bookkeeping. Okay. So this is showing the two in summary, right? Summary steps are here. That should not be difficult. By the way, why is all this interesting? Convergence goes from 1 upon t to 1 upon t square. Okay. 1 upon t to 1 upon t square is speed up. Huh? 1 upon epsilon to 1 upon epsilon square is not speed up. So please understand, don't get mixed up, right? 1 upon epsilon square should be brought down to 1 upon epsilon. But 1 upon t should become 1 upon t square. I mean, that is desirable. So there's a speed up. Both of these have brought speed up. I will refer you to my extra optional notes, very detailed notes, totally colorful. I mean, you love looking at how basically the Goldstein conditions also manifest in very complex ways. So the proof is there. You can actually prove. And what are the two exact steps? On the left hand side, you as I said, this is easy. The left hand side is easy. The Polyak is easy. You take the gradient at xt, descent at xt, and then just add a momentum mu times xt minus 1. So xt minus 1, but there's a multiplicative factor mu. So there's an exponentially decaying factor mu. So this is easy, right? The one on the left is easy. And in fact, let's write that down, since if you have understood the steps. So all we are doing here is xt plus 1 is xt minus, I've used okay, alpha. I've used alpha. So this alpha is the same as our previous eta. We used alpha as step size earlier, so this we have brought back alpha. Gradient is at xt plus the momentum based on how you have moved from xt minus 1 to xt. Okay. So the exponentially decaying mu from previous iteration. So this should be clear. The difference is here. However, when you consider the nested of momentum, as I said, the first thing you'll do is accumulate or consider a previous velocity term. So this is mu of xt minus 1, exactly the same term. Add that to xt. And then evaluate your gradient at xt plus mu times xt minus 1. So this mu is momentum. The same mu. Right? Here, see, while I used eta in the previous slide, I've used slightly different notations for step size here. One is alpha on the left hand side and eta on the right hand side. They may not be the same at all. This eta is the post momentum update gradient descent step size. It operates very differently. Okay, so let's write this down here. So here, the first thing I do is add this term mu xt plus mu right. xt minus 1 is a accumulated momentum. So there's an exponential decay that is going to happen with respect to all the previous xt minus 2, xt minus 3. And that is going to reflect now in your gradient update. The gradient is with respect to the decaying momentum. And instead of an alpha, I used a gamma here. And f is now evaluated on this entire thing. Xt plus mu xt minus XT minus 1. So this is the delayed gradient, deferred gradient. Okay. As I said, you just need a little bit of hard work for making sure that, I mean, it's implicit there, right? What you need to keep track of, but you need to work a little more carefully with Nesterov. Right? And as I said, the difference is there's an alpha with gradient f of xt, and the right hand side there's a gamma with gradient of f after the velocity update. Which basically is what we have summarized so far as gamma times the gradient of f at x nu. So what? I mean, that's not really x. It's not x nu, right? I mean, it's an x interim. If you want to call this to be more technically correct, especially when you implement, you may want to call this x nu as x interim. You call it x nu as a velocity updated x. That's all. Right? Okay. I think what I'm going to request you is as homework, write down the steps. So the convergence analysis in both cases, there's an inertia. While I said the results have improved, the results will improve in both cases to 1 upon t square. There's a slight difference in the multiplicative factors. So heavy ball for smooth and strongly. Oh, by the way, the results are not only for smooth plus convex. There are also results for smooth plus strongly convex. While the whole motivation was for smooth plus convex. As I said, the gap is explicit there. But even for smooth plus strongly convex, nobody has told you that the lower bound cannot get better. Right? I mean, there's some pathological cases have been found. So in both cases, analysis is done. Now it turns out that for smooth plus strongly convex function, it converges in square root kappa minus 1 divided by square root kappa the whole raised to t. Right? So there's a slight difference. Gradient descent was square kappa minus 1 divided by kappa. I mean, it's not like a major difference. But as I said, some of these multiplicative factors are changing. Right? So kappa has become square root kappa. So there's an important observation here that heavy ball momentum doesn't turn out to be very good for the smooth case. The first approach we showed, which actually takes the gradient at the previous iterate or the current iterate, and then adds velocity. As you might imagine, right? Basically, you are probably losing the advantage of a look ahead. I mean, you should have looked at gradient after the update. You're blindly adding velocity. So some look ahead is lost, and it turns out that it is not a very good choice for smooth case. But it turns out to be okay for strongly convex plus smooth. So if you have both strong convexity and smoothness, in which case you are the best of both worlds, right? So that's what we are showing here. For smooth plus strongly convex, we are doing almost the same, right? Raised to t, right? Or log of 1 upon epsilon, basically. Ts log of 1 upon epsilon. So that is making sense because you have both upper bound and lower bound on curvature. You know how much to anticipate to descend, even despite the fact that you are adding velocity in retrospect after taking gradient descent. Right? That was a problem in case 1, but not if the function is both smooth and strongly convex. Okay, but we'll continue the discussion next time. I think the homework problem, I repeat, is please try and write down the steps because this is what you'll need to implement. I mean, this or its variants. So please write down the steps for, especially for 2. 1 is very straightforward. We'll continue on Thursday. Thanks.